Hello everyone, welcome back. So, we started talking about the boundary conditions and we looked at what are the different boundary conditions which we usually encounter in our CFD course or computational gas dynamics course. Right. So, we will start with the wall boundary condition, which is the simplest one because it is essentially in terms of the variable the velocity, it is a Dirichlet boundary condition. But we will see that when you want to get the pressure or the temperature, okay, you may have to use the Lyman boundary condition, basically the gradient of the variable. Right. So, let us start with the velocity, which is very easy to think. Let us say you have a flow happening on a flat plate. So, what happens? So, the flow is happening. So, let us say I have a plate like this, okay, and then there is a flow which is happening from here, right. So, there are two things which you want to basically make sure. So, let us say if it is a simple axis, I say x and y, and this plate is aligned to the x axis. So, you have two components, okay, the velocity u and there is the component u and component v. U which is basically parallel to this and then v which is basically perpendicular to this, correct. If it is let us say more complicated system, let us say my plate is like this or something like this, then you have to find out what is normal, okay, u dot n, and what is tangential, basically u minus u dot n, whatever the normal component is subtract, you get the tangential component, correct. So, the one thing, the v, the velocity which is perpendicular to the wall, right. So, if you go very close to the wall here, so this is my wall here, okay. So, the one thing which is necessarily very important because it is a solid surface on the wall, so that the particles cannot penetrate the wall, okay. So, the penetration is not allowed. So, no particle can basically cross the wall here, okay. If it is crossing, then it is an interface, it is not a wall, right. So, that means there is no penetration is very important. Okay. And if you write in a mathematical language, then what about the normal component? So, this is my face and there is a normal component here. Okay. So, what about the normal component of the velocity that you have, that has to go to 0. Okay, sir, that is the no penetration condition. That means your u dot n or v dot n must be 0. Okay. So, that is the no penetration condition. Now, apart from this, you also have something called the viscosity in the gases. Right. So, you have like the gas molecules here everywhere, okay, and what they do basically they oppose the motion. So, you have the velocity here, let us say some value here, and as you go close to the wall. So, because on the wall, okay, if it is you are thinking about the flow happening, let us say a plate in a wind tunnel or a wing in a wind tunnel, on the wall the velocity has to go to 0, where that means the particle has to stick to the surface, right. So, my velocity is 0 on the wall here, right, and then you have a free stream velocity away from the wall. So, you have some flow coming on the wing or on the plate or let us say in a channel or in a pipe. So, what will happen that in that particular case, okay, I am making this diagram here. So, you have velocity which is the free stream velocity, let me call it u infinity, and then the velocity is going to 0 here, right. So, then there will be a boundary layer which will develop like this, okay. From 0 there will be some value, then it will increase till it will go to the velocity u infinity, and let us say if you are into the region, let us say this is my 0.99 of u infinity or 99% of the u infinity or 95% of the u infinity, this is called the boundary layer thickness. We have all studied this in our fluid dynamics course, correct. So, this is what you need to respect. So, if you are working with a gas which is viscous, okay, the viscosity will oppose the motion and it has to go to 0 on the wall and you will have this boundary layer formation. That means, on this wall your u velocity or the tangential velocity also has to go to 0. So, basically your u is also going to 0 here, right. And if you think of a, let us say I am talking about the 3D plate, okay, let us say I have a 3D plane like this, and I say my bottom one, this surface is the wall, right. So, my all the velocities has to go to 0, okay. There should not be any motion in this particular case if the flow is viscous, right. So, this is called the no slip boundary condition, okay, where we not only have the no penetration, but also the flow cannot slip on the wall, okay. This is called the no slip boundary condition. So, that means my all velocity components are set to 0 on the wall, and this is the simplest of the boundary condition that you can think of. You have all this, let us say if I have 2D flow, then my u is equal to 0, v is equal to 0. If it is 3D flow, then u is equal to 0, v equal to 0, w equal to 0, right. So, all my velocity components go to 0, u equal to 0, v equal to 0 and w equal to 0, right. And this is used in the viscous flow or the Navier-Stokes equation, because you need to have the viscosity, okay, in order to oppose the motion. Let us say when you are trying to do, I mean we have discussed a lot of examples with the Inviscid or Euler equations, right, without viscosity. What will happen if there is no viscosity? It will there is nothing to oppose the motion which is coming. Still there will be no penetration, it cannot the particle the gas particles cannot cross the boundary, okay. So, the normal velocity has to go to 0, my u dot on and v dot n has to go to 0, but the tangential velocity which is basically let us say in this case u, okay, in this case u, it will basically it will not oppose anything. So, whatever value that you have here, let us say my u1, this will also be the value of u1, right. So, the tangential velocity that you have needs to be extrapolated, okay. So, in this case let us say I have a 3D flow. So, only the normal will go to 0 and there are 2 tangential component. So, let us say my v is normal and u and w are the tangential components, okay, the slip components. So, they need to be basically extrapolated from the interior value, right. So, here is one example, let us say this is flow in a channel, okay. This is the slip condition where we are saying that you can see that whatever the free stream value that you have given, there is no loss here and the same value is maintained near the wall also, right. Where in the case of no slip, so it started with a let us say plug flow, basically the free stream value is assigned at the inlet, okay. This is my inlet, okay, and the flows basically the particles oppose the motion, it has to go to 0 at this boundary, okay, and the flow will start developing. This is at intermediate state, and finally, you will have this D profile which we always see, okay, on this kind of flows, okay. So, this is basically velocity going to 0 and then this increasing and at the center line it basically becomes the maximum velocity that you have, right. So, this is in the no slip. So, you can contrast this, so this is basically Navier-Stokes and this is Euler, right. Remember in both the cases no penetration condition has to be satisfied, that cannot be any penetration of the particle across the boundary, okay. But in one case you have slip, so flow is slipping. So, whatever value of the velocity that you have above that, the same value will be there on the wall also, the tangential velocity, but the normal velocity has to go to 0, right. So, yeah, you can have no slip for the moving wall also. For example, we have been talking about this lid driven cavity example. So, let us say I have this value here and there is a wall on the top which is basically moving, right. So, no slip does not mean that you will not assign the value of the movement of the wall. So, if I want to apply, so this is also wall, but now it is moving with certain velocity, right. So, what if you want to apply the boundary conditions in this case, for example, this is 2D flow, my u equal to 0, v equal to 0 on this side, okay. Here also u equal to 0, v equal to 0, here also u equal to 0 and v equal to 0, okay. What is this here? Here u equal to u lead, this is also no slip, but because there is a motion to the plate which have been given at the boundary. So, this is u equal to u lead and v equal to 0, okay. This is not the slip boundary condition. Remember, if the slip boundary condition would be there, then this u has to be basically extrapolated from the interior value, whatever value that you have has to be assigned there. This is no slip boundary condition, but with a moving wall, right. So, whatever the value that you are assigning that value there, correct. So, I wanted to make this distinction very clear because students are often confused. Okay, so now you have basically the velocity boundary condition assigned. But remember, we have talked about that in the case of compressible flow or even in incompressible flow, okay, you have basically u v w, then you have p, okay, in incompressible flow. In the compressible, you also have the density and the temperature, correct. So, let us look at this the pressure. How do you get the pressure here, right? So, you know the velocity, but you want to get the a bonding condition for the pressure. So, I am writing, for example, I will do first for the inviscid and then we will discuss the viscous also. So, this is my momentum equation, for example, written in vector form. Okay. You take a normal to this equation, okay. So, rho is a scalar, you take the normal to this, okay, and this is n dot grad p, and you are basically multiplying on the left hand side also, which is the unsteady term, and then you also have the nonlinear term. So, this is nothing but the pressure gradient, n dot grad p is basically what is the gradient normal to that, right. So, you have this gradient factor, this is a vector, and you are multiplying with the normal. So, you get basically getting this scalar quantity which is dp by dn. Now, you have this n dot du by dt and plus n dot u dot del dot u, right. Now, if you look at these terms individually, okay. So, un is basically the normal velocity, and we said that it has to be it has to go to 0, okay, whether it is slip or no slip, right. So, we will write u dot n is equal to n un, okay. So, you can basically take this you can interchange the derivative and the dot operation, okay, it's the vector operation. So, this is nothing but del un by del t, okay, because un is equal to 0. So, this will also go to 0, and if you look at the second term, okay. So, this can be written in terms of the slip quantity, and there are quantity. So, u dot n, so this is I mean you can elaborate it right in terms of the vector form, okay, and in simple you can write as u and v, okay. So, for u s equal to u and basically u n is equal to v, correct. So, see from this that you will have some quantity which is coming from the slip quantity, which is the u, and u n which is equal to v, right. So, this part is anyway 0, right, u n is 0, and now this is basically the stream wise gradient of the normal velocity, right. So, you have normal velocity, and we are talking about the stream wise variation of normal velocity, that will also go to 0, okay. So, that is why this will also go to 0 even for the inviscid case, right. So, because I am not saying that u s is going to 0, it can have the slip, but the gradient of the normal velocity vector or the normal velocity component with respect to the stream direction is also go to 0. So, this will also go to 0. So, the entire thing will go to 0 here, right hand side goes to 0, and that becomes del p by del n equal to 0, and which is ultimately you can write at the pressure gradient, the normal pressure gradient at the wall is equal to 0. So, now what we recovered is basically a Nyman bonding condition for the pressure, right. So, when the wall is viscous, so you can think of that there will be more terms here, let us say mu del square u. If it is compressible, then it becomes even more complicated, but ultimately you have some gradient, some double gradient of u and so on and so forth. Okay, you might have del to u by del x square, and then you also have del to u del x del y and so on and so forth, right. So, and you will have v quantity also, because del dot u is not going to 0, right. So, we have discussed about how the terms look like in the case of compressible flow, right. So, if you look at the viscous part, then you will have basically this part, okay, del p by del n equal to mu n dot mu del square u. But if you look at the Prandtl's boundary layer theory, and even here you can see that this operation can be interchanged, that becomes n dot u here, okay, this will become again u n, which will go to 0. So, yeah, this also can be related to the Prandtl boundary layer theory, which says that for high Reynolds number flow, the pressure remains constant across the boundary layer. This is one of the very important theory in the viscous flows, right. If you recall, if you have studied the fluid dynamics, you know that there was this D'Alembert's paradox, where they used to ignore this the complete effect of the boundary layer in the case of high Reynolds number flows, because they used to think that anyway the boundary layer is very thin. So, they are not impacting anything, but then they used to get this drag equal to 0, okay. and it was a major puzzle for a very long time until Prandtl came and he gave this boundary layer theory, and he basically derived the boundary layer equations, and he said that no matter how thin the boundary layer is, you cannot ignore it. In fact, if it becomes thinner and thinner, you will have gradients higher and higher, okay, and that cannot be ignored. If you ignore it, you will not get the drag. But then one part of that is that basically the pressure, this dP by dy is going to 0. Basically, the variation of pressure across the boundary layer is basically not there, right, and that is why in getting the pressure right in any CFD simulation is the easiest thing. Okay, getting other quantities like velocity and the vorticity or more complicated quantities are difficult, but the pressure gradient you can get very easily. The reason for that is that let us say you made a mesh which is you did not respect the boundary layer fully, okay, you did not make a very nice boundary layer grade, okay, still you will get a pressure reasonably well, and the reason for that is that the pressure remains constant across the thickness of the boundary layer. So, even if your boundary layer is not fully resolved, you might still get the pressure right, okay, but your velocity and all other quantities will go wrong. Okay, that is why the predicting pressure is the easiest thing in a CFD simulation. So, if you do a CFD simulation on any flow, you make sure that you first thing that you compare is the pressure. If your pressure is coming right, then only you are in the right direction. If pressure itself is not matching well, then there is some issue with your setup or your numerical scheme or your grid that you have made. Okay, you need to basically work on that. So, once you compare the pressure, then you can look at other quantities that you have. Okay, so this dP by dN equal to 0 is basically maintained for either it is viscous or inviscid, okay, whether it is slip or no slip, okay, for all the simulations that you have. Okay, so how do you implement it numerically? Okay, so for example, in the first order, so you have basically Pj plus 1. So, if you write this Taylor series expression, okay, so let us say I have my I and j. So, I is in this direction, let me make a grid like this. So, this is I and this is j, right, and this is my wall. So, this is my j equal to 1 and j equal to 2 and j equal to 1 is the wall. Okay, you need to get the pressure at the wall and you need to apply the Nyman boundary condition. So, what we will do is basically you write the Taylor series expression for this and simply P I j plus 1 and you write it around j. Okay. So, you have basically P I j plus delta n the distance that you have here, normal distance, and dP by dN which is basically the gradient, okay, which has to go to 0, plus del n square by 2 del 2 P by del n square plus higher order term. If you stick to the first order, ignore this, okay, all these things, and then you say dP by dN has to go to 0, that means that P I j plus 1 equal to P I j. That means you simply have basically, because j equal to 1 is the wall which you want to find out. So, basically P I at every point in this direction 2 is equal to P I 1 and you want to get the value at P 1. So, this is P 1 is nothing but equal to P 2. So, you need to just take the value from the next cell, that will be your next integer cell, I mean the first integer cell, okay, that will be your value at the boundary. So, that is the wall pressure, as simple as that. Okay, remember this is not a Dirichlet boundary condition, the P 1 and equal to P 2 we got it by using the Nyman boundary condition. If it is Dirichlet, then you have this P 1 equal to some P specified, okay, which we never do, almost never do on a wall. Okay. Of course, if you are inlet and outlet, then you specify all those things. Okay. So, if you want to go to higher order, then you can take 2 layers. This is my j equal to 1, j equal to 2 and let us say j equal to 3, right, and you want to get the value at j equal to 1. So, you write the Taylor series for j plus 1 and j plus 2, okay, and what you need to do, you need to because you are considering second order, you have to consider this term also. So, this is let us say this is A and this is B, correct. So, you multiply 4 into A and do minus B. So, 4 A minus B will become, so this is 4 P, let me ignore this I, j plus 1 minus P j plus 2 is equal to, this is 4 minus 1. So, 3 P j, and then this term will anyway go to 0 regardless of what term that you have, and this will also go to 0, because this is 4 delta n square by 2, this is also 4 delta n square by 2, right. So, now your P j will become P at j, which is j equal to 1, let us say, this will become 4 P j plus 1 minus P j plus 2 by 3, and if you j equal to 1, so this is P 1 is equal to 4 P 2 minus P 3 by 3. So, this is the second order value for the pressure, right. So, this is how you can implement. Now, the next thing is to how to apply the thermal boundary condition, right. So, for the inviscid flow you do not need it, because the wall is inherently adiabatic, okay, and the energy exchange which is happening is only through the work done by the pressure, okay. There is no internal energy component there, right. But for the viscous, you can have basically you will have the energy flux at the wall, okay, which may have both the viscous stresses as well as the heat conduction, right. So, you need to specify the temperature there. So, if it is isothermal, okay, then you are basically what you are saying that I know the value of the temperature of the wall. So, T w you know, right. So, basically you just specify this value. If it is adiabatic, then you have to basically say that okay, my flux at the wall I know. Okay. If it is convective, like we discussed in the last class, okay, then you know the convection formula, and you have to relate it with H equal to H t minus T infinity or something like that, and then you calculate the value of delta T, and accordingly you can. So, yeah, accordingly you can calculate the value at the wall, right. So, let us look at these two boundary conditions one by one. Okay. So, if it is isothermal, you just apply this T w is equal to whatever value that we have of the fluid at the wall, okay, and it also reflects because the velocity goes to 0. So, u and v and w all goes to 0. So, you can write your energy at the wall just CBT w, right. So, energy has two components, CBT plus half rho u square, okay. If it is 2D 3D, then it is like this, correct, because these things anyway goes to 0. So, energy at the wall is just CBT w, okay, and you can write, you can specify like this if you are using a ghost cell, okay. So, let us say this is my interior cell I, and I want to get the value of at the wall, and this is my ghost cell, okay. So, this is my one cell here, and this is my one cell here, and they are equally placed, they are equispaced here from here, right. And same thing you can apply in your pressure boundary conditions also using ghost cells. I am just showing one example. So, you want the value at this point is equal to T wall, right. So, how do you get this value? Let us say T face is equal to T wall, right. So, you need to have some value of the ghost cell. So, I will apply the T g is equal to 2 T w minus T I. So, you have the value as T I here, okay. Now, you add this T g plus T I and divide by 2, that will be the value of T f, right. That will be the value at the interface, this is my interface or the boundary, okay, wall boundary. So, if you use this value, this will become 2 T w minus T I plus T I by 2. So, then T I and T I will cancel and you will get the value of T w. So, this is how you basically implement these things in the boundary condition using the ghost cell. Okay. If it is adiabatic, then we are saying that the flux goes to 0. That means, using the Fourier's law, your the gradient normal to the boundary goes to 0, the temperature gradient normal to the boundary goes to 0. That means, it is simply if you look at the same case, the T g will become T I, right. So, that means, you basically you are, if you want to calculate the value of f I mean the value at the wall, okay, this is T f, or a better term will be T b, okay, the boundary value will be basically T g plus T I by 2, which is nothing but T I, okay. So, there is 0 heat flux, okay. Then now, once you have calculated these things, so one point I want to basically cover here is that let us say when a very high speed flows, okay. So, then it is very important to basically distinguish between the static temperature of the free stream and the temperature that wall actually feels, right. So, if you look at the definition of the stagnation temperature that we have discussed earlier, right. So, you know that T 0 is equal to T plus 1 by 2 gamma minus 1 m square. Okay. So, what is happening, let us say if a wall, okay, and then you have let us say some temperature here, let me call it T infinity, there will be a temperature boundary layer, okay, and basically when it comes to the wall, the velocity goes to 0, right. So, then the T infinity that you have changes to the stagnation temperature, and you should follow this relation, and you should be able to get the value of T wall, which will be equal to T 0, right. But that is not what happens in the case of very high speed flows. Okay. The reason for that is that there is a viscous dissipation there. Okay. So, they basically there are some losses because of this friction due to the viscous dissipation, and you cannot directly use this relation, okay, because near to the wall you have these particles which are basically dissipating some heat. So, your entire energy that you have thermal energy, okay, it is I mean entire energy that you have, the thermal plus kinetic energy, okay, this thermal plus kinetic energy does not get converted to the complete wall thermal energy, okay, there is some dissipation, there are some losses, and that losses is basically calculated using the relationship called the recovery factor. What is recovery factor? Is basically let us say if you do not have this opposition or the dissipation due to the viscous force, you would have basically T infinity minus sorry T 0 minus T infinity, where T 0 is defined like this using the stagnation relation. But now you are getting value which is less than T 0 because of this viscous dissipation. So, then let me call this term as T A W or T adiabatic wall minus T infinity. T adiabatic wall is at the actual wall temperature the wall is filling. This is also called the recovery temperature. So, then you get a recovery ratio or recovery factor, which is basically T A W minus T infinity and T 0 minus T infinity. This will be always bigger because T 0 is always bigger than T A W. So, this is always less than 1. So, that means you are having you are basically losing some of the energy due to the viscous dissipation. And then basically following the same formula. So, this is my stagnation temperature formula. Now, we will have one term which is multiplying to this, which is R. Okay, so this is 1 plus R gamma minus 1 2 into m square. And how does this R depends? This basically depends on the Prandtl number. Okay. And what is Prandtl number? Prandtl number is basically mu Cp by K. Okay. And you can write it as mu by rho, and this is K by rho Cp. I am taking this Cp at the denominator, and this is nothing but the diffusivity. This is the momentum diffusivity nu, and this is the thermal diffusivity alpha. So, it is a ratio of momentum diffusivity to thermal diffusivity. So, what is basically says is that let us say if P r equal to 1, then whatever the diffusivity of the momentum is basically being balanced by the thermal diffusivity. So, there are no losses and your R will become 1, but because of the Prandtl number value is not equal to 1, that means your momentum diffusivity is lower than the thermal diffusivity, especially in the case of let us say air. So, for the air the value of Prandtl number is around 0.72 or 0.71. Okay. So, then there will be some losses, and they are related. For example, in a laminar flow it is square root of P r, which comes to around 0.85 for air, and for turbulent flow which is cube root of P r, which is 0.89. Why it is why the higher heat is recovered? So, if R value is greater, then it is more close to the actual stagnation temperature. Why it is greater for the turbulent flow? Because you know that in the turbulent flows the mixing is mainly due to the eddies. Okay, it basically overrides the mixing which is happening due to the molecular viscosity. Okay, and that is why you basically recover higher heat in the case of a turbulent flow. Right. So, just to give you an example, so let us look at a vehicle which is flying at Mach equal to 3.5 at an atmosphere which is around 20 kilometer. So, at this temperature your I mean at this altitude your temperature of the atmosphere will be around 207 Kelvin, okay, which is around minus 56 degrees Celsius. Okay, and if you let us say you consider that there are no losses, okay, so this should be your ideal temperature that walls should obtain. and see it is very high compared to the value that we have here, because the Mach number is very high, right. So, although the ambient temperature is minus 56, you will be basically getting this value as around 690 Kelvin, okay, or 417 degrees centigrade. This should be basically T0. Okay. And if you have the losses because of the molecular diffusion, okay, you will have recovery temperature recovery factor here, and let us say consider a turbulent one, and then you will get around 690 Kelvin, right. So, first of all, the two things to observe here is that even if the outer temperature is very small, the wall feels very high temperature, okay, because of this adiabatic nature, and it can go to 417 degrees centigrade. So, you can think of any picture of a re-entry vehicle, and you can see that the temperature at the wall is really very high, okay, even if it is at very outer atmosphere. But then this is not the value that it will basically feel. Okay. So, yeah, so T adiabatic wall, there is some problem in this table. Okay. So, the T adiabatic wall will be around 690 Kelvin, it will not be the 749 Kelvin, it will be the 690 Kelvin. Okay. So, the wall is 59 degrees centigrade cooler than the stagnation point, correct, and that is because of the molecular diffusion, and this is because the air conducts some of the friction generated heat away from the surface faster than it can be stored, right. So, one important thing to remember is that if you want to get this recovery temperature right, in the CFD simulation what you need to do is basically you need to basically resolve the bond layer pretty well, okay, so that this molecular diffusions act on this, and it will give you the correct recovery temperature. If you do not make the bond layer mesh properly, you will not get the recovery temperature right, and if you do not get the recovery temperature right, you will not get the heat flux right, because the heat flux is defined as this, okay, T w minus T adiabatic wall, okay, and not this T w minus T 0. Okay. So, this is how basically you can make your simulation correct. And the last thing is the density. So, once you know the density, I mean you know the pressure using the dP by dN equal to 0, you know the temperature, okay, either adiabatic. So, in the adiabatic you have dT by dN equal to 0, or if it is isothermal then T equal to T w, correct. So, if once you know the present temperature, all you need to do is use this relation, the ideal gas law, the rho w equal to P w by R T w, and from there you can calculate. If it is adiabatic, then both are basically gradients, okay, dP by d equal to 0, dt by dn equal to 0, that actually leads to d rho by dn equal to 0. You can also calculate using directly the this relation of adiabatic wall. Okay. So, this way you can get the density. So, now we have seen the different wall bonding condition, the slip bonding condition, no slip bonding condition. We also saw how to calculate this the density and the temperature and the pressure on these boundaries. So, with that I will stop. In the next class I will start with the symmetry bonding condition and the periodic bonding condition, and subsequently we will go to the far field bonding condition. Okay. Thank you very much.